Today we are going to talk about one of the most important constants in mathematics, the number e. You may have seen e before when talking about exponential functions and logarithms in an algebra class, and wondered why anybody cares about it. The answer to that comes from calculus, and we will see why through the course of this chapter. For now, we're just going to start with the definition, or at least one possible definition for e, the one that's going to be a little bit more useful for us in this particular class right now. The number e we're going to define through a limit. Specifically, we're going to take the limit as x goes to 0 of the function 1 plus x to the 1 over x power. So that's an interesting function here where there's actually not only x's in the base but also in the exponent. So it's kind of a combination of a exponential function and a polynomial, kind of in a weird sort of way. Now, we can't just plug in 0 right away. We can't do that. If we try to plug in 0 on the bottom, in the base here, we're just going to get a 1. And you think, well, 1 to any power is just 1. But if we plug 0 into the exponent, well, 1 over x goes to infinity. And you think, well, something to infinity is probably going to be infinity if what we're actually taking the exponent of is bigger than 1. So like 2 to the infinity, you think, well, that is obviously infinity. We're multiplying 2 together infinitely many times. Or if what we have inside here is between 0 and 1, you might think, well, it goes to 0 because, well, like 1/2 to the infinity power. Well, you're taking 1 divided by 2 to the infinity, and you're going to get 0. Infinitely many 1/2s multiplied together should become 0. So it's in this weird spot between things that should be going to infinity and things that should be going to 0. So does this become 1? Does it become infinity? Does it become 0? Well, it turns out this is another one of those what we call an indeterminate forms. Whenever we're taking a limit and we get something like 0 over 0, infinity over infinity, these could be positive or negative infinities. If we get infinity minus infinity, but then there's also ones that involve when there's an actual base and an exponent that are both changing, and you get various indeterminate forms from that as well. If we ever get something like this, that means that things could be a lot weirder, and we have to take a step back and try other things to try to figure out what it actually goes to. Now, in this particular case, until we have the number e, there's not really any way to find a limit for this thing. We actually are defining e to be that limit, and we can go ahead and actually graph it and see that even makes any sense. Let's take a look at the function 1 plus x to the 1 over x power. We get this particular curve here. It's actually a pretty nice looking curve for the weirdness of the function. And we see that at 0, it does actually just seem like it hits the y-axis at a point. And that point is approximately 2.71828182846. You get a point just right there. This is actually an irrational number. It's kind of like pi in that sense, where there's not really a nice way of writing it other than just kind of writing it as some sort of limit. It does seem like it has a nice pattern at the beginning, but then it breaks that after a little bit. So it can be kind of easy to remember the very first few digits of it, but then after that things just get weirder. But the point here is that this is a number that's going to be kind of useful to us. And we'll see it get more useful as we go through some of this calculus. Now let's see where this particular function came from. It's kind of a weird function. Why do we even care about it? Well, it boils down to what we call compound interest. Let's say we deposit some amount P. This is our principal into an account, and we have an annual interest rate of R. But we don't just calculate interest every year. We calculate it a certain number of times per year. Maybe it could be monthly, maybe it could be weekly, whatever we decide it's going to be. We're going to just say that that number is going to be in. So I guess when it comes to talking about this, instead of just saying it's calculated, we can say it's compounded. Now, the point of compound interest is that every time you calculate interest, you calculate based off what the current amount in the account is, rather than what you started with. So simple interest would be taking the principal, and then every so often you add a fixed amount based off what that initial principal is. With compound interest, after you've added on interest the first time, the new interest the second time is going to be based off not only what the principal was, but how much additional interest was put into the account after that first time. So the interest kind of builds on itself as it goes. And that's actually a little bit more sensible when you think about accounts like bank accounts where the money could be changing over the course of time. They don't want to just remember some initial amount and try to calculate interest based off of that. They want to just look at what is in the account, and here's the interest based off that amount. Well, what that actually means is that we are going to, every time we compute interest, we will multiply. Well, we're going to take the annual interest rate, divide it by the number of times per year. But we don't want to multiply by R over N, because we need to also include how much money is being left in there from before. So we're going to add 1 to that. So 1 plus R over N is going to multiply each time we take interest. And so we're going to get the compound interest formula that the amount in the account at any time is going to be the amount of principal times 1 plus R over N times the number of times that we've actually compounded it. But we're going to write that as the number of times per year times the number of years that we've dealt with the account. So you can think of this as a function of t. Maybe I should write it that way. The amount in the account at year t is given by this. Now we've written this as more of a kind of a continuous type function. Technically, when we're doing compound interest, we're doing it at these at very discrete times, so the amount that's in the account will jump up at different intervals. So this works as long as we're at some sort of when n times t is some integer. But we're going to treat it as if it is a more continuous function because that's a little easier to work with. But the natural question at this point is, what if you just calculate interest more and more frequently? Essentially, just what happens if we make n really, really big? Well, we can compute that as a limit, and we're going to treat it as a limit as n goes to infinity. We're going to take the limit as n goes to infinity of our formula. What happens to this function as we do that? Well, the first thing, we're treating the principal as a constant. So we can pull that out of the limit. The limit doesn't really care about that part. Second thing, I'm going to actually change this nt that's in this exponent here. I'm going to change it so that I can have an r. I don't want r there. Still going to have the in, but I'm going to have an in over r, but I'm going to take this thing to the rt power. So remember, because of our laws of exponents, when we have a stacked power like this, we get to multiply the n over r times the r over t. And that just simplifies down to n times t. But one of the properties of limits is that if we have a power here that doesn't involve the actual variable that's changing, so we don't have any n's in the rt, when we have that limit like that, we can actually pull out that power. So we still have the 1 plus r over n to the n over r power, and this thing, that whole limit, is being raised to the rt power. You get to pull that power out as long as there's no n's in it. And now we can just focus on this particular limit and what this limit actually does. Now, to make it simpler for us, we're going to make a substitution. We're going to make a new variable, which I'm going to call x, and that x is going to be the r over n that we have here. That's going to allow me to replace the r over n with an x, and then the n over r, well, n over r, if r over n is x, then that's 1 over x. But we still have to change the n that appears in our limit. What is x doing if n is going to infinity? Well, if n is going to infinity, we're getting infinity on the bottom. The r is not changing, so the x is going to go to 0. So x goes to 0 as n goes to infinity. So we're going to change the limit down here. And now look what we have. We have the limit as x goes to 0 of 1 plus x to the 1 over x. That is exactly the function, the limit that we have right here. This number inside here is by definition e. So we have p times e to the rt power. And you might have seen this formula before in one of your algebra classes. It's pretty famous as the formula for continuous compound interest. But the point here is that this limit of this function came up in this calculation, and that is one of the reasons why we define this to be a particular number. Now, it's not the only reason that e is useful, but it is definitely one of the places where it pops up where you might not really be expecting it. Now, in this particular class, most of what we're wanting to use e for is as a default base for an exponential function. We want to talk about f of x is equals e to the x. This function is so important, especially in calculus, that people sometimes call it the exponential function and give it a fancy notation, exp of x. If you don't want to write this as an exponent, we can write just exp of x, and that's the exponential function. The book actually titled this section as Natural Exponential Functions, and so I'm guessing that's what they wanted us to name this function, the natural exponential function. But they didn't actually explicitly state that somewhere, or at least I couldn't find it. So I'm not used to calling it that. I'll probably just refer to it as e to the x, or the exponential function, or something like that. The reason why the natural that is there comes into play more often when we get to logarithms. We'll actually be referring to a natural logarithm that's going to be based off of this function. But feel free to use that term if you prefer. Now, one other important thing here is that computers and calculators do know this function very well. Your calculator should have a button for e to the x, or at least for e itself, so that you can combine it with the x to the y power button. Take for instance the Windows calculator. It has a button right here for e. If we want to take e to the fifth power, we can go ahead and do that. That's what the value of this particular function is at 5. It's 148.41, so on. Now, you might be looking around that you don't see just an e to the x button on this calculator, and some calculators are like this because of that. But because we do have the e here, we can kind of circumvent that. But one thing that you may not realize is that this calculator does have a specific e to the x button. Look for a button that has ln on it. If it doesn't have just an e to the x button by itself, usually if you press the second key, it will turn the ln button into an e to the x button. So instead of having to press e and then press the XY button and then put in 5 to get it, I can simply just push 5, and with the second key pressed, I can press this button, and it immediately puts e to the fifth power. We get the exact same value. So if your calculator does not have a button specifically for it, this is how they usually have it. But if you have a scientific calculator, it's got to have this function in some form or fashion on it. Now, of course, as an exponential function, we can graph this function. Remember, here e is about 2.7, so on. So it is a number that is bigger than 1. So we know its graph is going to look something like this. So this is y equals e to the x power. It has specific points on here. It has 0, 1. Every exponential function has that point on it. Then we have the point 1e. Remember, e here is about 2.7, so 3 would be about here, and 2 would be about here. So it's a little closer to 3 than it is to 2. Of course, we also have points like 2 comma e squared. We have -1 comma 1 over e. All those kind of points are on here. But it's always got this kind of a shape. And it has all the same properties. It's continuous everywhere. It goes off to infinity on the positive infinity side. Goes to 0 on the negative infinity side. All that kind of stuff. But before we get into doing actual calculus, there's not a lot that we want to do with this function right away. The book does talk about using the exponential for modeling, specifically modeling things like population growth and stuff like that. But we're going to have a whole section on exponential growth later in this chapter, so I don't really want to spend time doing that right now. Maybe we'll just go ahead and end this section with a problem about interest. Let's look at problem 29. The instructions here are complete the table to determine the balance A for $3,000 invested at a rate R for T years, compounded in times per year. So we have $3,000 invested. That's going to be our principal amount. Specifically for the one that we're doing, so that was the general instruction for a set of problems. In 29 specifically, they give us an interest rate of 4.5% and a time span of 30 years. And then the n is from our table. We have a table. We have n here. We have a here. We want to fill in spots for 1. So 1 time per year, 2 times per year, 4 times per year, 12 times per year, 365 times per year, and finally, continuously. So if we think about these numbers were not chosen randomly. This would be if you're only going to compound your interest once per year. It's a yearly compounding. This would be semi-annually. This would be quarterly. This will be monthly, daily, and then obviously continuously. Now, we're going to have to treat the continuously separate. That is a separate formula, though it's based off the one for the other ones. So remember, our formula for the first 5 of these here is going to be A is equal to P times 1 plus R over N to the NT power. Keep in mind here, R is 4.5%. Well, that really means that R is 0.045. That's what the percent means. We have to divide it by 100. T is 30, P is 3,000, and we just go ahead and compute these things. So, say for N equals 1, we're going to take 3,000. We're going to multiply it by 1 plus, well, if we're adding 1 to 0.045, we go ahead and just take 1 and attach on the 0.045. And we're going to take that to the N, which is, again, 1, times T, which is 30. And, of course, we're going to use a calculator for this. I'm not going to do this by hand by any means. 1.045 to the power of 30 times 3,000. We get this particular value here, 11,235.95. Of course, that is in dollars. And so that's what we should get if we only compute interest once per year on this $3,000. But we're doing it 30 times because we're doing it once per each of the 30 years. For N equals 2, so we still have the 3,000. That doesn't change. Now we're going to have to take the 0.045, divide it by 2 before we add it to 1. So you take our 0.045, divide it by 2, then add 1 to that, which of course just puts the 1 in the first spot. So we have 1.0225. But because we're doing it twice per year over a course of 30 years, we're going to compound interest 60 times. And then we just go ahead and put this into our calculator. We've already actually found out the base here, so we just raise that base to the power of 60. We multiply it by 3,000, and we get 11,400.40. I should probably actually be putting these numbers here. And I'm going to be running out of space on all this. Moving on to N equals 4. Still have 3,000. That doesn't change. This time we get to divide our 0.045 by 4 before adding 1 to it. So 1.01125. This time we're doing, well, N times T. N is 4, T is 30. I'm just going to multiply those together to get 120. That's the number of times that interest has actually been computed on this principal. So I take this amount, raise it to the power of 120, multiply that by 3,000, and we get 11,485.38. Now we move on to 12. So I'll have 3,000. We need to take our 0.045, divide it by 12 this time before adding 1 to it. So we're getting some pretty small numbers now. Or small, I mean the R over T part's getting pretty small. So we're going to get 1.00375. Of course, we're taking N times T. T is still 30. We're going to multiply 30 by 12. We get 360. So we take this to 360 power and multiply by 3,000. 11,543.09. So you might note so far, every time we do this, every time we pick a bigger in, we are getting a slightly bigger number, but they're not really increasing as much as you might think they are. So the first one, even going from 1 to 2, we gain not even quite $200 over that 30-year span. Then it wasn't even a full $100. This one because we went from 4 all the way to 12, it was almost as much as going from 2 to 4, but it still wasn't that big of an increase. What if we go all the way to daily? 365. We still have the 300 here, or sorry, 3,000. We're going to take our 0.045, divide it by 365, get a really small number here. This is actually in scientific notation because there's so many zeros in front of it. When we add 1 to that, it'll kind of fix that so we can see it a little bit better. There's 1.000 with some stuff after that. 1.000, and so on. Because we're dividing by kind of an annoying number here, it doesn't really terminate like it did on the other ones. Our power here, if we take 365 times 30 years, I'm just going to go ahead and give us that. It's 10,950, that many times. And I calculated that separately beforehand just because I want to have this value that we're using as our base and use it right away without having to type it back in. That way I can be a little bit more exact about it. So I'm going to raise that to the 10,950 power. Big power there. But we've got a pretty small base, and so it doesn't really get that big. Our answer is actually not really that big compared to what we had here. It is not even $30 more than what we already had when we did it monthly. We get 11,571.31, which we'll go ahead and put in our table. Finally, if we were doing it continuously, now we use a different formula. We're going to use the A equals PE to the RT formula. Remember here, R is still 0.04, T is 30, P is the 3,000, 3,000 E to the 0.045 times 30. It's going to be a lot easier to type in than it was for n equals 365. So let's take 30 times 0.045, get 1.35. That is the exponent, so I'm going to take second e to the x and multiply that result by the principal of 3,000. Get 11,572. Let's round this to 2.8. And we put that in our table as well. I read off the wrong thing in my notes. 72.28. So, we've been letting n go to bigger and bigger numbers. We noticed that as we went, we got smaller and smaller increases. Even going so far as going from 12 to 365, we only went up less than $30. But then going from 365 to infinity, which is what continuously really is doing, we only really went up by about $1. So, might think, well, why bother? Well, calculating it continuously was actually a lot easier than calculating it daily. We had to deal with this 365, which gave us a really big exponent and a really small base, and in fact, we have to assume that our calculator is pretty accurate with those numbers, which if we give it a really tiny numbers, it might start rounding things off, and so things can get a little bit iffy. But we can actually even kind of just estimate what we have for 365 if we use the formula for the continuous compound interest, because these are so close anyways. So if nothing else, we're using a simpler formula, even if it is an e to the something, an e to the x type function. It's something that calculators know how to deal with very, very easily and nicely, and it's a formula that's really easy to plug numbers into. So for ease of use, maybe that's one of our reasons for using e. In the next section, we will actually start talking about differentiating the function e to the x. And there's where we'll start seeing where we're using a base of e is actually really important. Because we actually will have some trouble differentiating something like 2 to the x for a little while. We need to talk about logarithms before we can even do that. But e to the x is actually nice enough that we can actually do it. So meet me in that one, and we'll get to have a brand new function to differentiate. So see you there.